Hey, welcome everybody to week 2. So, as you may think, on Wednesday last week, we saw the zeroth law of black hole mechanics. Then on Friday, the first law of black hole mechanics. So it comes as no surprise that now our next target is the second law of black hole mechanics. That's also known as the area theorem. And that is fundamentally different to the first two in the sense that for the first law of black hole mechanics, we had stationary spacetimes. So we had so there were properties of horizons, of Killing horizons. For the area theorem, you probably know the statement. The statement is that the area of the event horizon, that is to say that what Dominic had as straight H on Friday, that thing can't decrease as you move to the future. So as the intersection of your Cauchy surface moves to the future, that the area of the intersection can't decrease. So that's a statement of the area theorem. So this is clearly dynamical. So we cannot be pondering with, we cannot be contemplating only stationary spacetimes. So it's different. And then the definition of the event horizon that we had on Monday last week, that thing is finally going to play a role. And the immediate concern is that, well, if the area theorem concerned something about the event horizon, and the first two laws were dealt with Killing horizons, how do we know they're doing the same thing? And that's a legitimate concern, and this is not an easy matter. It's quite involved to establish the connection between these two notions. But for us, I think it suffices to remember the uniqueness theorems that Dominic mentioned. So then we can rest assured that at least in the Kerr-Neumann family of solutions, those things must coincide because we identify the event horizon independently a Killing horizon, and for the Kerr black hole, for example, that the one that Dominic wrote, you knew that there was a vector field which was Killing and tangent to the horizon, and that generates a Killing horizon and also an event horizon. Okay, so all that said, so let's focus on the area theorem. Let me just start by saying that we will not get to the end of the area theorem today. That's going to be on Wednesday. The good news is that most of what we're going to talk about today is also useful for the singularity theorems. They are almost identical. And that was the reason why Penrose got his Nobel Prize 3 years ago. All right. So let's start sharing my screen. So the first notion we're going to construct here is that of a congruence of geodesics. It doesn't have to be geodesics. Things much simplify if they are. So we are only going to consider congruence of geodesics, but in principle, it could be congruences of arbitrary curves. So the idea is, if you start with a curve lambda of t, and at one point of this curve, well, the tangent vector to this curve that we started with is z. So at a certain point, you look at another vector and look at the geodesics that crosses that point with tangent vector v. And you should just drag that vector v along this curve and lambda of t, you get congruence of curves. So a point lambda tv, so what I write here, is you obtain from the starting curve, from the base curve, and then you move along a finite parameter v along the integral curves of v, and then you've got a congruence. So by construction, the derivative of z along v is going to be 0. So so I like the introducing congruences like this because it's very constructive. It starts from, so you can very easily visualize what's
sorry, it was not very clear, but is V any arbitrary vector field, or how are you defining V?
Yeah, if for now it is. Because we are going to do it in geodesics, they are going to be tangent to geodesics, but it could be any vector that commutes with Z.
Okay, you require it to commute with Z. Okay.
That's right. That's right. Yeah. So that's the alternative way of seeing this is okay. So let's drop this requirement of having a preferred curved out of which I'm constructing the congruence. Let's start with a family of curves. They're going to be geodesics, and that just let's find a vector that commutes with them, and you have yourself set up for studying these congruences. So yeah, so the intuition here is to think of a family of geodesics in our case that they are close together, and because that's what we're going to do. You're going to study how this vector Z behaves as you move along this V's, the congruence and the congruence of itself. Here we are here going to deal with no geodesics specifically. It's almost everything is almost identical. If you're looking for time lag congruences, yeah, just minor difference here there. For example, well, I can mention some of the differences, but it's very similar. In one sense that they are not similar is that it's more ambiguous to define parameter along no geodesics. And that's what I write here, because if V is an affine parameter, then any f of t times V is another affine parameter. So define parameter, there's no way of fixing define parameters as you move from one curve to the next. So that's fine. That's just one ambiguity we have to deal with. Okay, and also because V is null, so the subspace orthogonal to V includes V itself. So that's very standard. We even made use of it previously. So what we do is say, well, we are not really interested in parts of vectors that are parallel to V itself. We want to see this thing that is orthogonal, that's measuring the distance between neighboring geodesics. That's what we really want to study, not the tangent component. So what we have to do is say, no, let's not look to the entire orthogonal subspace, but let's take a quotient. So you define an equivalence relation between two vectors if they differ by a multiple of V. And then you take the quotient of that space with respect to this relation. So you have so you have a dimension 2 space now. And you can project vectors onto that subspace. That's what I'm denoting by SPN here. Now, you can be very constructive about how you make these projections. And this is a construction that I have. Okay, if I just scroll up, you will identify that's very similar to what I did here for the bifurcation surface. So again, I chose I picked the other null vector, which is normalized with respect to V. So I denote that by L. So in the product between V and L is -1. So then this tensor HAB here projects. So this is, again, I'm using this round brackets means the symmetrization between the indices. So HAB is GAB plus VALB plus LB, excuse me, plus LAVB. Then you can work out by inspection that this HAB does the projection that we wanted. So it'll project. I'm not sure why I denoted this orthogonal here. Just imagine it. Yeah, just pretend it isn't there. I don't know why I did that. So this projects. Take a generic vector and projects that. So as a tensor, it's going to have 2 0 eigenvalues. So that's tantamount to the fact that the subspace that we want to deal with is two-dimensional. So that's an important difference between null geodesics and time-like geodesics. Time-like geodesics, the subspace would be dimension 3 because you don't have to take this quotient. Okay, so this introduces. So yeah, so as I said, 2 of these eigenvalues are 0, but the remaining 2 are not. So this introduces a Riemannian metric on this SPM. Okay. All right, so let's start studying how this vector Z, the separation vector, behaves. So the first thing is, by definition, the derivative of it is 0. So I'm writing this as a commutator. So this is just a statement that the commutator between Z and V is 0. So they commute. So you've got this dv of Z. The covariant derivative of Z along V is the covariant derivative of V along T. T is this. Yeah, this is how T is defined. So from that, I'm writing this explicitly in terms of, just projections of the gradient of V. Now let's take a second derivative along V. So that's why I write it here explicitly, and I use equation 1, which is just the condition that the derivative is 0. So that's what I did in this step. Now I'm going to just expand the derivative, like so. And when the derivative hits this, so this has two derivatives of V. So what I do is I use the definition of the Riemann tensor to flip the order of these two derivatives here. So that's what I have in this equality here. So I rearrange that. So I rearrange the sum. So by doing so, I get you get the derivative along Z of the acceleration vector. But because these are geodesics, this is 0. And I'm left with the curvature tensor, determine the curvature tensor. So that's very nice. So this leaves us with this equation is famous even in other contexts because it provides with a geometrical interpretation for the curvature tensor. You see that the curvature tensor is measuring how nearby geodesics move. So if you're so this equation, as I said, if you're not dealing with geodesics, you still could have some on an equation, but that would have acceleration terms. So it's a little bit more complicated. So this is sometimes called Jacobi equation, sometimes it's called the geodesic deviation equation. This name is rather intuitive of why. Now, on top of that, we know that, well, by definition of L, the normalization with V, the projection of L onto V is a constant, so the derivative is 0. And if you work out how the inner product between Z and V propagates along V, and you just expand it, and you use the symmetry, the commutation relation, you see that it's also 0, which means that, well, it's not entirely unsurprising, but you mean that you can form a basis at one point, and you can parallel transport our basis. So in particular, we can take Z to be orthogonal to L, and in that way, it is a purely space-like vector at a point P. And so then you propagate at the purely space-like vector. At this point, it's convenient because we might not have, so to simplify our notation, we don't have to distinguish between the vector Z and its projection onto SPM in what follows. Okay, so let's look into the solutions of equation 1 and realize that, well, this is just, once you write it as well as I have here, you realize that this is a first order linear ordinary differential equation. So the solutions must be of the form Z is a certain matrix that I'm denoting by E, capital E, times the initial value at a point Q. Right, so then I can, I'm not trying, maybe I should use a different set of indices because I don't want to convey the notion that this E, capital E, is a tensor. because they define at different points, but just think of it as a matrix. So I can treat these equations as an ansatz, and I can plug it in equation 1, which is just the commutation relation, and I can plug in the Jacobi equation and read how these equations look for the matrix V as a function, for the matrix E as a function of V. So these are the equations that you get. Right? So that's from the commutation, and this is from the geodesic deviation. At this point, we introduce a bunch of definitions, which is just a way of decomposing the gradient of V. So this is the composition. So let's go on the term by term. So I have a gradient of, so the entire information is contained in the gradient of V. And so now what we're going to do, we're going to take the symmetric part of that, and when you construct and you project onto this dimension 2 space, and this is denoted by theta AB. I don't think this has a name. Sometimes it's referred to as expansion tensor, but I'm not sure how many. If that's correct. Its trace does have a name. This is just denoted by theta. This is called the expansion of the congruence. The anti-symmetric part, so if I took the symmetric part and I take the anti-symmetric part, and that is called the vorticity tensor, or the, how is it? There's another name for it. It escapes me now. Twist. Sometimes it's called the twist as well. So it's an alternative name for omega AB. There is a symmetric trace-free part of this. So, then I take theta and I remove the trace of the part that is, so that the trace of sigma is 0. And here again, this 1/2 is because the space we in question has dimension 2. If these were time-like geodesics, they would be 1/3, just to remove the trace. So this combination receives the names of shear tensor. And interpretations are more or less, you might be familiar with the interpretation of these quantities from, for example, fluid dynamics. So you can see that because, so this is so theta is an expansion, it's a trace, so it measures how much things contract or expand. The shear, so you preserve the volume, but it might squeeze in one direction or another. And the vorticity preserves the shape, but it creates a rotation, right? So this is you can think, in hydrodynamics, they are, you can build an intuition of what they do there. So if I take the full gradient, I can express that full gradient in terms of these quantities. So it's gonna, so I can recompose what the full gradient is by adding together all these objects, and that's what I have here. Now, if I have this decomposition, I may look at the evolution equations that I had here, 3 and 4, not for the entire gradient, but just for these combinations, for the expansion, the expansion, vorticity, and shear. So let's do that. So here on the left-hand side, I have the equations that I got from the first derivative of E, so the ones that I'm pointing here in my cursor, for each of these 3 quantities. And on the right-hand side, I have the second derivatives that I get from this other equation that I labeled number 4. So let me not do it. Well, it's relatively straightforward, and that's what I have written here. The one identity that you might have to dig out, if you don't remember, is this identity that I had here, the trace of, well, if A is a matrix, and so you have this identity here, the dx of A times the inverse of A is one of the determinant of A times the derivative of the determinant. You might see that this works if you pretend that this is if you imagine that A is the diagonal matrix, and then you can convince yourself that this works, but otherwise you could open up the definitions as well. This is somewhat similar to the identity relating the exponential of the trace and the determinants. Okay, so these are the equations for each of these parts of the gradient. Now, one thing to notice is, well, the dv of the determinant v is not singular, because otherwise you run into trouble with this equation here, right? So if this is not singular, it means that, yeah, so from this equation, it means that if the determinant of E goes to 0, you got a divergence in theta itself. Okay, so that's something to notice. And another consequence from this equation that I have here, from the right-hand side, is that, well, this is just saying that this thing and the brackets is an integral of the motion. So it's a constant along each of the geodesics. So it's particularly interesting is what happens if at one point, let's say that point Q, you happen to have E equals 0. And then it is going to be, so this entire thing is going to be 0 everywhere, including points in which E is not 0. So the only only way this to be true is this omega is 0 everywhere along that geodesic. So that's an interesting characterization. For the following reason, we are interested in characterizing so-called conjugate points. A definition of a conjugate point. Okay, I know I'm going a little bit fast, but I'm trying to connect this in just a second. So a definition of a conjugate point, P to Q, if the P and Q are points in a certain geodesic, if there is a Jacobi field, a Jacobi field is a field that obeys the Jacobi equation, so a solution to this equation, that is 0 at P and Q without being 0 everywhere. In other words, these are points in which you start from neighboring geodesics, so they depart from P and they reconverge to Q from this infinitesimally close geodesics. And this is particularly interesting. Okay, so first thing is we know that this happens in gravity because, for example, we observe this quite frequently when you're looking at telescope images and you see gravitational lensings. You see multiple images of the same source. So this is a manifestation of the existence of conjugate points on all geodesics. So there's yeah. Now, why I say that this property, the second property I wrote on this page is interesting, is that if I'm using this technique of congress of geodesics in order to find conjugate points, then I assume it has to be 0 in either Q or P. So for these congresses, I know that omega is 0. Omega B is 0. So that's a way of getting rid of the vorticity, just like that. There is a second way of getting rid of vorticity, which relies on the Frobenius theorem. So if you read Wald's textbook or Eric Poisson's relativist toolkit, that's how they argue for the purposes that are going to be relevant just in a minute. That's how they argue that you could get rid of the vorticity in a congress of geodesics. And that's true, because if you have a hypersurface orthogonal congruence of no geodesics, then the vorticity is 0 regardless. But I like this. Well, first, I don't want to talk about the Frobenius theorem because it's already dense. The 6 lectures are already sufficiently dense. And second, because that's, if for our purposes, we are trying to look for conjugate points. So you can get rid of the vorticity just by, for this one reason. We assume that the Jacobi field has to be 0 at one point. Okay, so now let's multiply the equation 4, which is the equation containing the curvature tensor, by the inverse of E, and take the symmetric part to get an equation for theta AB. So that's the symmetric part of the gradient projected. And that's what you get. Right? So there's a, this is not a difficult exercise, but that's what you get. And I can take the trace of this equation, and then I get the evolution for theta, the expansion. And that's what I get. That's the equation for the expansion. How the expansion changes as you move along the congruence. I understand that this equation was discovered independently by Landau, and I was told this name is pronounced Raishalduri. If I'm butchering this name, please feel free to unmute yourself and say how I'm supposed to pronounce his name, or simply Raishalduri equation. It contains less information than the equation above, because it just contains the trace of it. Okay, so that's, here I say what I had been saying before. If I'm looking for conjugate points, and I know that if for conjugate points, I'm going to look for points in which the expansion blows up. So, and I realize that this is the only term. Well, okay, there is this term here, when I'm going to talk about it, the Ricci term, the Ricci curvature term, which I'm going to talk about in a second. And then there is this vorticity term, which appears with an opposite sign with respect to the shear and to the expansion. So if we're looking for conjugate points, then this term is 0. And the Raishalduri's equation simplified to this. Now, let's entertain the possibility that this contraction of the Riemann of the Ricci tensor is nowhere negative. Let's just entertain this possibility and see what happens. Well, then it's saying that this derivative is strictly negative and bounded by the value of the square of theta itself. So I can integrate this equation, and I realize that from this, if V naught is the point where it started, so this is the initial value defined parameter. So this is an upper limit for the value of theta at every point. So, in particular, it will blow up at a finite value, right? So when this V becomes this number, it blows up to minus infinity. So if, well, as long as this thing is negative. So if this initial value of the expansion is negative, it means that the expansion will get to minus infinity at a finite distance. Yeah, and here a caveat, of course, provided that the geodesic can be extended that far. Perhaps the geodesic dies before you reach that value, and in which case you don't get it. But you found the criterion for finding conjugate points. If this condition is true, and if the initial value of the expansion is negative at your initial point, then you know that there is a conjugate point. Okay, nice. So now let's talk about this. What is this doing? Well, why would I expect? Is this physically reasonable to expect that this contraction to be nowhere negative? And I claim that it is, for the following reason. Let's take the statement of the null energy condition. The null energy condition states that the contraction, it's similar to that, but instead of having the Ricci tensor, I have the energy momentum tensor. And this in a space-time in which the null energy condition holds, you have that to be non-negative at every point, and for any null vector v. If one uses Einstein's equations to express the curvature in terms of the energy moment, the Ricci curvature in terms of the energy momentum tensor, because v is null, this is equivalent to the condition we had before. So if the null energy condition holds, then you have this condition satisfied. But then you might say, okay, well, 6 of the one, half a dozen of the other. Why is this any better? Well, because we have some interpretations. Energy momentum tensors, we talked about energy momentum tensors, but before we talked about general relativity. We know what they represent. So there is a condition called the weak energy condition that says that the same contraction that I have here holds not for any null vector, but for any time-like vector v. So that, because we interpret it, so now if it's for a time-like vector v, then I can imagine that then a certain observer is following the curves parallel to v. So if they are following the curves parallel to v, so this contraction is proportional to the energy density as this observer sees at any given point. So the weak energy condition is this statement that this energy density is nowhere negative, which in classical physics seems entirely reasonable. And actually, there's something even that seems even more reasonable in that there's something even stronger that seems reasonable in classical physics, which is called the dominant energy condition. And unfortunately, I didn't write it here. So let me just stop sharing for 1 second. The dominant energy condition says that the contraction of T so this vector, or minus this vector, that represents energy fluxes. It's everywhere. It's time-like or space-like and future direct. Sorry, it's nowhere space-like and it's future directed. This is called the dominant energy condition. And if you build an intuition, say, well, I know that the good thing about energy momentum tensors is that they are covariantly conserved. So in a very small neighborhood of a certain, or in which the conservation equation looks like the flat Minkowski conservation equation, then I know that that represents the energy flux, and the energy fluxes, just by virtue of causality, had better not be space-like or pointed to the past. So that's like the condition. If that is true, and so that is stronger than the weak energy condition, and if the weak energy condition is true, then because if you assume that the energy momentum tensor is continuous, then the null energy condition has to be true as well, because you make v time-like approaching the light cone at every point. So these are reasonable assumptions, at least in classical physics. These are reasonable assumptions in classical physics. If you start building up field theories, in classical field theories, and you start with any couplings and potentials, then you can start violating any of these equations. Is this a matter of alarm? Is this cause for alarm, or it's case by case scenario? And in fact, it's not even, for example, if you are someone who wants to see things very cleanly and are not convinced by this local argument, you may say, well, it's not even clear to me that in curved spacetimes, the dominant energy condition implies that the energy fluxes are not space-like. True, well, this was intuition built in plot, but in fact, you can prove it. The way to prove it is you assume that the energy momentum, you impose the dominant energy condition, and you assume that the energy momentum tensor is zero, exactly zero on a set S, and you can prove, well, it might take a couple of pages to prove it, but you can prove that if it's zero on S, and it obeys the dominant energy condition, it's also zero on the Cauchy development, the future Cauchy development of S. So that's just to say that if something has to enter, it has to enter via time-like, non-space-like curves. There's another condition which is useful. Remember, that's all came about because what appeared in Cauchy-Arderus's equation was a contraction with the Ricci tensor. So it's valid to also consider, well, what happens if I'm studying here, and we are only studying no geodesics, which is for the area theorem, that's what matters. But if you're looking for singularity theorems, sometimes you don't want to say, you look at points in which no geodesics are incomplete, but you might be interested in what happens with time-like. Are time-like geodesics also incomplete? And then you will have to go through finding conjugate points and all that. So then it's very useful to say, well, how happens if I assume that not the energy momentum tensor, but the Ricci tensor contracted with two time-like curves, two time-like vectors, the same time-like vector twice, I should say. Can I say something about the sign of that thing? Well, all I can say is that it has a name. If you assume that this is called the strong energy condition, I'll give you an interpretation of the strong energy condition in a second, but I just wanted to mention that this is not equivalent to say that the weak energy condition, because now the GAB is not zero, the GAB terms after contraction is not zero. But I wanted to mention that before I go back, because I had a Venn diagram here on top, so you can visualize the implications between these various energy conditions. So SEC denotes a strong energy condition, DEC the dominant, WEC the weak, and NEC the null energy condition. So you say either the strong or the weak energy condition, they both imply the null energy condition, but there is no mutual implication between them. And the implication that I had mentioned before between the dominant energy condition and the weak energy condition is also represented in my diagram. But let me give you an interpretation for the strong energy condition. Let me go back to my screen share. And this is actually, you can interpret it from Cauchy-Arderus's equation itself. It is, so you see that if the matter content is encoded in R, and then there's the statement that this contributes negatively to DD.
Excuse me.
Yep.
Sorry, I want to know about the Casimir effect. Is it related to the null energy conditions or the strong energy conditions? Because I heard something about the Casimir effect in the vacuum, and I wanted to know that it's related something about it with the null energy conditions or no.
Okay, good. That's an excellent question, because well, the Casimir effect is a quantum effect. So all these plausibility arguments that there was stating had to do with the classical theory. In fact, and I said that you could, in the classical theory, for certain couplings and for certain potentials, you could start building up violations of all these energy conditions if you want to. But in quantum field theory, which is the case of the Casimir effect, then these violations happen much more easily. You can have physical fields, for example, in the Casimir effect is a great example because it's an electromagnetic field. So it's a field that's realistic in all respects. And in the vacuum, in the Casimir vacuum, you have a violation of all these energy conditions. All of them are violated. So it's natural. Okay, let me just say something else. I don't know if you remember, but on Wednesday last week, when I was discussing the zeroth law, I said that I did not want to use the original derivation by Bardeen, Cartan, Hawking, because they imposed, in 1973, they imposed the dominant energy condition on the horizon. And because I know from studying fields around in curved backgrounds, I know that this is untenable. This is just not going to happen in quantum field theory. Even in classical field theories, for example, you can get evaluations of these equations for fermionic fields in curved black holes. Well, as classical as fermions can get, but you can get very violations there as well. So for that reason, I didn't want to use the original derivation by Bardeen, Cartan, Hawking. Our derivation did not impose any energy condition, but it made use of the existence of a bifurcation surface. So we knew that the kappa was constant along geodesics, but we need to go through to the bifurcation surface to see that the derivatives across different gaps. So as you move across the bifurcation surface, and on that surface, the derivative was also zero, then to combine to say that it was null inside the horizon. So you're absolutely right. In quantum mechanics, in general, in the quantum theory, none of these energy conditions are to be taken as reasonable, physically reasonable. Now, there is a lot.
Thank you very much.
Yeah, no worries. Yeah, so but if you're worried about the possible consequences of the violation of these energy conditions, they are plenty. But there are also other results in quantum field theory that say that these violations are not as wild as you might think originally. For example, if you take not a pointwise, not this an equation like this in a point, but you integrate it over the entire curve, then you can place bounds. So it can't be an arbitrary negative, the integrals. But at every point, it's unbounded from below. You can get arbitrary violations of these.
Doctor, excuse me, because also in the wormholes that we have a null negative energy, we need to have a truth. I asked about this one, that the derivative goes to the zero and the surface, and I thought that about the Casimir effect and about the non-energy conditions that you said, I had I little confused beforehand, and now I could understand about that. Thank you very much.
No, you're very welcome. No, these are very relevant comments. That's why I spent quite a fair bit of time on them, because these are relevant questions. And actually, yeah, let me leave it like that. Okay, but as I was saying, so there is an interpretation. So if you want to say, so the interpretation of the strong energy condition will have to do with the sign that appears in Hershey-Aldoudy's equations. So that's a way of saying that, interpreting, roughly speaking, that gravity is attractive. So that's an interpretation for the strong energy tensor. That's curious, because it looks like it's not identical, but it's very similar to what appeared when Dominic wrote the Kolmar integrals, not as definition of mass, for example, was -1/8 pi, the integral of Hodge d psi, not this integral, which is on a surface at infinity, but the part of this integral, when he decomposed it in a volume term plus the terms in the horizon. So that had to do with the matter term. It was very similar to what appears there. So it's not identical. If the space-time is not only static but ultra-static, then they become almost identical. But it's similar. So I wanted to just point out that everything makes sense here. So that's an interpretation from the strong energy condition, gravity being attractive, and also provides an interpretation. Actually, Hershey-Aldoudy's equation is nice because it also provides and the fact that vorticity contributes negatively, I mean, not positively, should I say, He also says that that intuition that you might get, so you have vorticities, things spinning, that thing contributes to something like a centrifugal force. Well, this is all intuitive. Don't take that any seriously. Yeah. Okay, so before moving forward, I should also mention something about the first law of black hole mechanics here. That's not what we saw on Friday. Certain derivations, okay, so there's actually a derivation or the first law of black hole mechanics. It's not the same thing, but something that is calligraphically the same as the first law of black hole mechanics. By calligraphic, I mean all the symbols are the same. If you look at the equality that Dominic wrote and reinterpret each of the symbols and change the assumptions, the equation is still true. That thing was actually written by Hawking and Hartle, or Hartle and Hawking. I think Hawking and Hartle in 1972. So even before what Dominic showed you, that it's calligraphically identical. Let's just briefly comment on that. That is derived as follows. Yeah, there's a question.
Yeah. So, like the conclusion that you draw that gravity is attractive. This was also based on like Einstein validity of Einstein equation. Like you go from R A B V A B V this inequality greater than or equal to 0. You come here from energy condition via Einstein equation. So if let us say, can we reach here without using Einstein equation? And this attractive nature property of Einstein validity of Einstein equation will be.
Yeah, okay. I don't know if I understood the entire question because there was a little bit of background noise, but let me repeat what I got and then you let me know if you're satisfied with what I'm going to say. So I think you're already the following. Okay, what appears here to give you all these interpretations for the energy conditions, except this strong energy condition, I was appealing to Einstein's equations. But what happens if my theory of gravity is something else? So do I have this interpretation? No, you don't. But you still have this geometric characterization. So and sometimes people, okay, physicists like to call them energy conditions. People working directly into Lorentzian geometry sometimes call them geometric conditions, and that's because they see it's a condition. It's a condition of the Ricci curvature. So the energy condition for the null energy condition. If you don't want to talk about Einstein's equations, it's just a statement that this is non-negative when VA and VB, when VA is an arbitrary null vector. But everything stays the same. The weak energy condition, yeah, that's a little bit different. But the strong energy condition keeps its interpretation, and the null energy condition just happens to be interpreted in terms of the Ricci tensor itself. Yeah, and that's actually related to the point. Okay, does that answer your question at all, or did I speak something entirely different?
Yeah, partially. I mean, if you are imposing this geometric energy condition RAB VV greater than or equal to 0 directly, then does it not mean that we are imposing that gravity is attractive? It's not a consequence, but we are imposing that.
That's right. That's right. Yeah, that's right. Yeah, that's what you read directly from this Landau-Haichaduri equation. That's right.
Yeah. Okay. Thanks.
You're welcome. So yeah. So let me comment on this pseudo. Pseudo might sound pejorative. Let me not call it that. But this alternative version of the first law, and the derivation goes as follows. So you look at the Haichaduri equation and imagine what happens if you start from a Kerr solution and you treat the energy momentum tensor as a linear perturbation. If you treat it as a linear perturbation, all these terms, the vorticity squared, the shear squared, and the expansion squared, we're going to be a higher order in the energy moment, in the perturbation in the energy momentum tensor. So you neglect these terms, and you're left with an equation like that. For the black hole, for a curved black hole, as you saw from Dominic on Friday, I know what the tangent to the horizon is. It's psi plus capital omega times psi. So psi is the time-like, and the time-like killing field of infinity, and psi is the axial killing field. So you write that and you integrate, and you use Einstein's equations to write this in terms of B. You call the delta M, you call as the energy flux as on the horizon, across the horizon. Delta A now it's not the same delta A that Dominic was talking about. Delta A now is this changing the area of the congruence, and delta J is the same. It's the flux of angular momentum. And you integrate that and impose it, that the black hole is eventually going to settle down. And you get something that is exactly, the symbols are exactly the same as the first law of black hole mechanics, the ones that you saw on Friday. But they are completely different two theorems. First, the assumptions are different, and more importantly, what the symbols mean are different. That's why I like to call the version that you saw on Friday the global, the first law of black hole mechanics, and the one that I've just described by Hartle and Hawking, Hawking and Hartle, the local version of it, because that has to do with every point, how things change, and you just integrate that at every point. The fact that these equations coincide is in itself something nice, because at least it shows that there is this local version of the first law of black hole mechanics is at least self-consistent. Because if you had given out, so if the fluxes of energy across the horizon, the flux of angular momentum across the horizon, and the expansions happen to have a different relationship between them, then different to what Dominic showed to you on Friday, then we would be in trouble, because if we first had to assume that things, if you throw matter into a black hole that is stationary, it would settle down to a stationary solution. But then I get something that is not how the parameters M, J, and A relate, and when you get a family of stationary solutions and of Einstein's equations that represent a black hole. So then we would be in trouble, because then we point out a certain inconsistency between these two, between this local analysis. So it's nice that it's not like that. So I'm not proving, but I'm telling you how to do it. So you linearize Rayleigh-Schauder's equations, you use Einstein's equations, you integrate them, and you impose suitable conditions and then the integration limits, and that's how you get something that is identical. In certain analysis, when you want to go beyond the classical theory, it's interesting to look at both versions. It's interesting to look at what Dominic said and what this one is. Yeah, okay. Let me go back to my screen share. Yeah, I also should say that it's possible to generalize the global version of the first law of black hole mechanics for other theories that are not general relativity. It played a very important role. Einstein's equations did play a very important role, as you remember from Friday, but it has been done already. It has been characterized. Other geometrical theories of gravity and the first law of black hole mechanics, well, something similar to the black hole. The area, I mean, the expression for the entropy might not be exactly the same, but it is characterized for any differential covariant theory of gravity in greater generality. And here,
just a small question there. So I know of the proofs where they look at perturbatively, like at different orders of the perturbation parameter, they prove the first law. But is there a generic proof like all levels of perturbation parameter?
All levels of what? Ah, you mean that it's not linearized?
Yeah, right.
Ah,
So I
uh-huh.
know that recent work by Harvial and Hollands have proved it up to the second order. But is there a proof that goes beyond that?
Not that I know of. Not that I know of.
Okay.
But again,
Thanks.
but this is the local version, right? And I think what I was trying to convey here is that the global version is stronger than that. The one you saw on Friday,
Right.
you can keep that. Yeah, that's not linearized. That's just a family of solutions, and you compare.
So yeah, so those are the like GR like solutions, like I mean, where you still have the
Yeah.
Einstein like equations.
Well, yeah, it doesn't have to be Einstein's equation, but it has to be different covariant. Yeah, but yeah, then you have that. Yeah.
Okay.
Ooh, okay, right. So there were some side comments here, but let's go back to what you were saying before. So I discussed that. Okay, now I'm going to state a theorem without proof, because if I were to prove this would take an entire lecture to prove it. So I think you'll forgive me for not proving it. This has to do with idea. Okay, so let me give you an idea of how these theorems go. So even if I'm not proving, at least you know that's not taken out of his sleeve, but there is a rationale behind it. So I'm going to reuse this diagram that I have here, but don't read the captions. Just look at the picture. So imagine I have these 2 points, Q and P, and let's not think of Lorentzian geometry. Let's just think of Riemannian geometry. Forget about S, just look at P and Q. And let's say, well, I have a geodesic between Q and P. And it so happens that there is a conjugate point, R, in between these two. Then you may think, so this curve, the geodesic that I started with, might not be minimizing the length. Because if there's this conjugate point, so this other curve that I write here, going from Q to R and then straight to P, has to be the same, has to be the same length. So what happens if I just round, there is this corner here, there is this cusp here. So if I round it, I might have an even shorter length between them. And that's this type of ideas. First, they can be formalized. You look at the length and the variation of the length of the arc length in first order and the second order. So you take two derivatives of that, and they can be generalized it can be applied to Lorentzian geometry as well. Now, needless to say, because this all has to be formalized, and you're dealing with curves that are not smooth, so the derivatives become discontinuous. So needless to say, proofs are going to be laborious, and yeah, so that's why I'm not going to that. So in Riemannian geometry, a more closely analog to the statement that I have here is that if I have a surface and so the geodesics that extremize the length between, so they minimize the length between a certain point and the curve, they have to be geodesics. They have to be orthogonal to the surface, which, I mean, this is even true in Euclidean geometry, right? So what's the distance between a line and a point? It's going to be orthogonal, and it's going to be a straight line. So up to that, no surprise. But it's also true that if you have a conjugate, in order to minimize the length, you can't have a conjugate point in between. So this is the result in Riemannian geometry. There is a result in Lorentzian geometry that if there is a conjugate point, so now if S is a space-like to surface, and there is a conjugate point R between there, then there is a variation in the sense of the arc length variation that I was just describing before, that gives you a time-like curve between S and P. Okay, so that's something that I hope, at least with this analogy with the Riemannian geometry case, that at least this doesn't sound like something outrageous and intuitive. We're going to use this not today, but we're going to use it on Wednesday. Today, I wanted to do yet another thing, which is okay, so let's start with the following setup. Let's look at a point Q, and let's look at all the points on a given surface S, which are the distant, well, as far of Q, the distance between that point and Q is always sigma, and it's a constant. So what I wrote here in this dashed line, this looks like an hyperbola, but yeah, because you know we're talking about Lorentzian geometry, and you wanted the vector connecting Q and the point, you want it to be time-like as well. So that's why I'm drawing it as a hyperbola. So let's look at what happens at this point. So you have a set of points here, and you have these vectors that point from Q to one of these points in the set. And then I'm calling on the surface of constant sigma, I'm calling DDS this tangent vector that's connecting to Q, and DDT a tangent to that surface. Okay, yeah, I hope the setup is somewhat clear. So let's see what happens with the derivative, with the inner product between these two fields, these two vectors, as we move along the surface. Well, okay, so I'll just use the regular product rule here, what I said. Okay, this term is 0, and so you live with this term. What to do about this second term? Well, I write the commutator. Instead of writing the commutator, I'm writing as the Lie derivative between these two fields, and I putting back the term that I had removed, and I realize that on S this is going to be 0. So that says that DDS, the covariant derivative along S of DDT, is the same as DDT of DDS. This is referred to as the symmetry lemma in some cases. So if I combine these two results, I get this statement here, right? So DDS, so how this inner product vary, it is using the second equation on the first is DDT of the vector itself, so it's 0. That means that along this set, the inner product is preserved. But because at Q DDT is 0, it means that this two vectors are orthogonal in the entire surface. Okay, so this is. So let's put in a sentence what we just saw, because so let's put it right in terms of a single sentence. And I write here, the time-like geodesics through Q that are orthogonal to the surfaces. Yeah, okay, so this is hard to say in words, but that's, well, not really. This is just the statement I said. It is a collection of all points in P that they are distant at a certain cost. So I'm writing this in terms of the inverse exponential maps. So the inverse exponential map on P is a vector. So that's vector X here. So this has a constant value of sigma. Of course, this is all true in a certain normal convex neighborhood of the points, because these exponential maps have to be well defined. But it's okay. So sufficiently small neighborhood are preserved. Okay, so let's say what happens the following. So let's imagine that I have a convex normal neighborhood of a point Q, and let's think of yeah. So let's suppose that from Q to P I can connect these points using a non-space-like curve. Well, to begin with, let's imagine that it's a time-like curve. Okay, so let's see what happens. Well, so then by what we saw before. Okay, so let's think of the following. Let's see what happens with the vectors that emanate from Q, right? So if I think of here I'm making an identification between a curve, the tangent vector, and imagine the curve that I have in space-time with a curve in the tangent space. But it's always that is to say, it starts. So this at a point Q, this vector is originally time-like. So let's say at sigma, at a given point, on this curve gamma, there's going to be a point. There is going to be a surface that shares the same value of the distance sigma with respect to Q. That surface, and that surface, by what we saw in this previous result, I claim that this surface has to be the value of sigma along the different surfaces that I'm sticking at every point of the curve. I claim that the value of sigma has to be decreasing. Well, first of all, the value of sigma has to be negative or zero. It's zero at Q itself, but it has to be negative because, well, if this vector is what we saw, at least at the beginning and close to Q, at least close to Q, it holds this previous result. So it has to be negative. But then I claim that the succession of these values of sigmas as I get these surfaces, as I move these surfaces along the curve gamma, have to be decreasing. Why? Well, if suppose it isn't, if it isn't, there is going to be at least one point in which it's zero because the derivative is zero because it starts from zero and it decreases. So if it starts increasing again or it stays constant, so that means the derivative is zero. But that can't be because at every point of the regional curve gamma, d dt is time-like. If d dt is time-like, this can't be. So that means that these curves are always decreasing. Well, so that means that once I reach P, this is going to be in the surface like this, so that P can also be reached by a geodesic. So this is okay. So this notation means the section of the tangent space on Q in which the vectors are time-like. So CQM is a part of the TPM in which the tangent vectors are time-like. So it means that I can reach P from using a time-like geodesic as well, if it can be reached by gamma. So it's even more important. It's not what happens when it can be reached by a time-like geodesic. But let's say it can be. Yeah, and I also should say that what I'm arguing here is assuming everything is smooth, but it's also true if you have this piecewise C2 curves as well. So this can be generalized. I'm not doing this here, but it can be generalized, and it's sometimes useful because if you want to combine arguments of this sort with these arguments, but I'm not doing this here. Okay, so if gamma, so I start supposing that gamma is time-like. What happens if gamma is not time-like but still causal? So it's not space-like at any point. Okay, so now let's repeat this argument, but for a different vector, not ddt, but ddt plus an epsilon times another vector. This vector is taken to be the following. So take the vector, take y in the tangent space of P of M, so that the induced exponential map is time-like, and furthermore that the inner product between y and ddt is negative, so that the integral curves for ddt plus epsilon times y, and you see that these integral curves for every epsilon, this is negative because well, either ddt is negative and we're done, either it or it's zero, and if it's zero, this term gives you the negative sign that we're looking for. And this family of curves is continuous with respect to epsilon and also to the base point. So then I repeat the analysis that I had not with ddt, but with ddt plus epsilon times y, and I conclude that P can be reached by the closure of that of this set, right? Because it's non-negative, so it can be zero, but it cannot be positive. So, this is somewhat intuitive. So then it means that it can be reached by the closure of the time-like vectors from I started in a Q, so they can be reached by a non-space-like geodesic. If I know that this curve is certainly not a time-like, and then if it's null at every point, then I know that's a null geodesic. So that's what I write here. So if P in a normal convex neighborhood of Q can be reached by a causal curve from Q that's not time-like, then P lies on a null geodesic from Q. And I think you are suspecting where you're going to. And a final remark that is a corollary of the first statement, the chronological past and futures of P. Well, this is for the future, but same holds for the past. Are open sets, and we're going to use that as well. And the idea is, well, if there is a point that can be reached, I can keep reaching at a point, and they are all, if can be reached by geodesics, right? So if I take the geodesics at a point, and I know that I can vary continuously arbitrarily to a certain point at a certain boundary, but I can get arbitrarily close, and they mapped into the exponential maps. So they're open sets. All right. This is what I had for today. And I know it was a bit dense, but I'm open to any questions that you might have. And this intuition that we're going to build up to is, of course, this is all from the definition of the event horizon. So we're going to see that event horizons are null geodesic. So that's why we're talking about this, because that's going to, well, we are going to put this all together on Wednesday. But for now, when we stop here, and I'll take any questions.
Hi, Bruno. I just wanted to ask, you mentioned that you could use Raychuduri's equation to derive or pseudo derive a the local version of the first law, right?
Mm-hmm.
Could this also be done for a Kerr-Newman metric, or
Yeah. The only thing is that instead of V being psi plus omega times psi, you've got to have to find I don't remember from the top of my head what's the generator of the null geodesics of the Killing horizon of Kerr-Neumann, but yeah, you could.
So it doesn't matter that there's now electrovacuum, since we assume the energy moment intensity to be linearized, right?
That's right. Yes.
Okay. So it's just
there's a separation between what's background and what's a perturbation in this local derivation, but the first law of Black Hole mechanics, right? Because am I still audible? Can you hear me?
Yeah.
Oh, okay.
Yeah,
good. Yeah, because it froze for me, but maybe it didn't freeze for you. Yeah, so there is a separation of what is background, what is perturbation. So in this case, in Kerr-Newman, you treat the electrovacuum as background, not as a perturbation, and you think that there is a perturbation on top of that. Yeah.
Okay. Thank you, Bruno.
You're welcome. Anybody else? Okay, well, there's something in the chat. Let me see what there's. Oh, okay, so that's not a question. All right, so if there is nothing else, so I'll see you again on Wednesday. The plan for Wednesday is to complete the proof of the area theorem, because as you saw, we didn't quite get there, but we will. And so that's going to be just half of the lecture. And the second half, we're going to finally say, well, if this is about thermodynamics, let's just chat a little bit of how this laws of black hole mechanics translate into thermodynamics. And this will entail, for example, violations of energy conditions, violation of the area law, evaporation, and this sort of things. And finally, the last lecture is going to be about the physical aspects of evaporations and how black holes behave at thermodynamical objects. So I'll see you on Wednesday, and take care. Cheers.